Hello to my best chemistry students. Right now I'm making this video and thinking about you and hoping you're having a good time at the homecoming dance. I didn't even see what the game was yesterday, so somebody's going to have to give me that score at some point. Now, we have our three quantum numbers that, whoa, there's a typo for you. Three quantum numbers that tell us at least a 90% probability of finding an electron with a given energy. And now we're going to talk about a bonus one that was found through some spectroscopic investigation. And that is the spin quantum number. And what we find is that when you have a particle that is moving with any kind of, or an angular momentum, and hopefully you learned this in physics, this motion generates really an internal magnetic field. Whoops, magnetic field. Let's get this right. Magnetic field. Now, the electron spin is quantized. What can happen is that the magnetic field of the electron can actually interact with an external magnetic field, and splitting of lines was seen. And this splitting was into two parts. So we see that the electron, what we call spin, is quantized. It has only two values, plus 1/2 and minus 1/2. Now, normally, these orientations are considered degenerate. Degenerate, not what you're thinking about. I have a good comic on that, so remind me to show you a really cute comic on degenerate electrons. Degenerate means they have the same energy. That's very important. We're going to come across this concept later on when we get into bonding. So you want to get that word down well as a vocab. Degenerate, same energy. Now, each orbital can hold 2 electrons. And what we do is we give the first one an m sub s, or spin, of plus 1/2. That's the numerical value. And we are going to link that with an up arrow as our symbolic model. So numerical model, symbolic model. Then the next one that goes into an orbital will have a minus 1/2 spin, and we'll use a down arrow for that one. Actually, I tend to use half arrows, but full arrows are just fine as well. Now, where we get these spins is that when electrons are placed into a magnetic field, the first electron that goes in will align itself with the magnetic field, and that's the one we call plus 1/2. And the next one will align itself against the magnetic field. We call that minus 1/2. Now, the analogy I like to use for this is if, say, you're in a railway car and there's only one bed. Now, most girls, if you're, on a band trip or whatever, most girls have no trouble, sharing a bed. But guys do. I mean, my sons with their cousins had 2 queen beds. There were 4 of them. Each 2 of them had a queen bed by themselves, and the other 2 slept on the floor. Just don't get it. And so guys do not want to do this. And so when guys have to, if forced to share, they have been known to sleep so that one person's head is at the top and the other person's head is at the bottom. And that keeps them within their comfort zone or minimizes repulsion. So that's what we'll be looking at here, is the types of things that are going to minimize repulsion. And so that's how they found this spin quantum number, which gives us a bonus way of describing and understanding an electron. And not only that, what's going to be really cool is it's also going to give us some information about particular functioning of elements, some elements. And remember, structure determines function. So that's where we're headed with that one. Now, let's take a look at some examples. This is You Do It 9, so that's where you should be in your notes, is on You Do It 9. I should change these to We Do It. So we're on number 9. And it says answer the following questions. Now you want to be really careful about the wording of these. You notice that this says P sublevel. All right. Now if it's talking about the P sublevel, I know I'm talking about L. And if it's the P sublevel, L is equal to 1, which means then that M sub L has 3 possible values, -1, 0, +1. Now each of these, each orbital, so these are the orbitals, right, at this level, that's an orbital, that's a sublevel. Now each of these can take 2 electrons. So 2, 4, we don't put them in this way, but I'm going to do that for now, 6 electrons. So that sublevel can take 6 electrons. Now I want you to go over and count the boxes on the periodic table from boron to fluorine and see if you notice anything interesting about that whole block. It's called a representative block of elements from boron to fluorine and then, excuse me, boron to neon actually, boron to neon, and then on down, just out of curiosity. Now, the next one says, what is the maximum number of electrons in the d orbital? Now, some of you are going to see that word d and say, wow, if I had d, that means M sub L was -2, -1, 0, +1, +2. You're going to put 2 electrons in each. So you're going to go 2, 4, 6, 8, 10. And you'd be wrong because it didn't ask for a d sublevel. It asked for a d orbital. And it doesn't matter whether it's a p orbital, a d orbital, a s orbital, an f orbital. All orbitals hold 2 electrons. And so really the question is digging in there to make sure you understand that difference in terminology. Now the next question said, what is the maximum number of electrons in n equals 4? Now there's a variety of ways you can do this. So if I have n equals 4, and I'm going to go ahead and erase some of this. Let's get rid of some of that so I have some room. If n equals 4, we know that we can have L equals 0, so we have S. L can equal 1, so we have P. L is 2 and we have D. L is 3 and we have F. The S has 1 orbital, so for M sub L there's only 1 orbital. P has 3, D has 5, F has 7. So this can hold 2 electrons. The P can hold 6. The D can hold 10. Just as an aside, take a look at your transition metals in the middle there and count how many blocks are in those transition metals. And the F has 14, and so then we can add all those up and we'll get 32. Or it is talking about the whole energy level. You can remember that formula that we had earlier that said 2n squared. So 4 squared is 16 times 2 is 32, and it's a lot faster to get at that answer. Up to you. You can kind of go the long route and figure it out, or you can go a shorter route. Now this next one is telling us to write the complete set of quantum numbers for each electron in the 3p sublevel. Now you have a table in yours, and I'm just going to write it on the side here. So if I have a 3p sublevel, that means that we have 3 orbitals, right? Because if we have p, that means L is equal to 1. That means M sub L is -1, 0, +1. Now, we can put 2 electrons in each, and it asked us to do the complete set. So we have to assign this for all 6 of those electrons, right? So that's the task. Now, this is 3p. That means every electron in here has n equal to 3. Now, since it's a p sublevel, it also means every electron on there has L equal to 1. Now, we're going to get a little bit of a distinction because these two electrons have m sub l equal to -1, these two have an m sub l equal to 0, and these two have an m sub l equal to +1. Okay, so on your table you should have 3, 3, 3, 3, 3, 3. And then we would have 1, 1, 1, 1, 1, 1, because L's the same. Now for m sub L, we're going to have -1, but how many electrons can have m sub L -1? We have 2 electrons. So 2 of the electrons have -1, 2 of the electrons are 0, and 2 of the electrons have +1. Now, when we get down to the level of m sub s is where we'll get a key distinction. For m sub s, the first one would be +1/2. The second one's going to be -1/2. +1/2, -1/2. +1/2, -1/2. Wow, I'm really squeaking that in on you. Didn't leave myself enough room for that one. But I hope you got to see that. I want you to notice something very important here. All of them do have the same value of n. All of them have the same value of L. 2 each have the same value of m sub L, but no 2 electrons have all 4 quantum numbers alike. That's a very important concept. Notice that in that whole sublevel, no 2 electrons had exactly all 4 the same. They always at least differed in that spin, and that's a very key concept there. Now let's look at a few more of these before we shut this video off. We want to take a look and evaluate whether these orbitals exist. So will they exist in a way that allows our attractions to be maximized and our repulsions to be minimized? So for this one, n is equal to 3. P, if we have a P, that means that L, so for P, that means L is equal to 1. Now, that's allowed. L can take on values all the way from 0 up to 2, actually. So that's good. You need to justify your answer, and showing this is part of your work, and then making your statement of what L is allowed to be when n is 3 would be a good statement to make. Now in this case, n is 2. If we have F, that means L is equal to 3, and that's not allowed. The maximum that L can be here is 1. Right? Because 2 minus 1 is 1, so the maximum L can be is 1. So that's not allowed. For S, n is equal to 4, L is equal to 0, and that's okay. 1p, n is equal to 1, since we have a p, and write it down if you need to. Write 0, 1, 2, 3. Stupid people die first. So if I have a P, that must mean L is equal to 1, and I can't have that. The biggest L can be, the upper boundary is n minus 1, which is 0. So that can't be. The max is 0 for that one. So that doesn't work. So putting the designations there is good, but also in your justification, you want to make some sort of a statement about L going from 0 up to a max of n minus 1. Now let's take a look at these. This goes to the m sub L level. So when I do these, first I start with n and then I check my L. So in this case, L is 2. What that means, n is 2, that means L can be 0 and 1. Can't be 2. That's out. You want to say this in words. I don't have time, and you don't want to be as bored out of your mind as this typically is and have me write out statements. I'm not really worried about m sub L at that point because L knocked me off. Now, in this case, n is 3, so that means L can be 0, 1, and 2, so we're good. That's fine. Now, if L is 0, that means the only thing m sub L can be is 0. M sub L can't be -2. So that's out. Now, the next one is cut off a little bit. This has M sub L equal to +3. If N is 6, L can be 0 up to 5. And so 2 is okay. We're good with L. If L is 2, M sub L can only be from -2 up to +2, right? And all integers in between can't be +3. So that one's out based on our M sub L criterion. So you'll need to be able to answer questions like that. And we're now ready to move into some mathematical models of how we depict atomic structure using the tools that we have built. And if you're having trouble with this section, if you didn't understand it, I want you to call me over to your table so that I can re-explain it to you. So for now, this is YBCT signing off.